Previously, we analyzed the class C amplifier with an FAT, which is an active element, and there's an LC tank, if you recall, which provides the flywheel a free energy storage effect that when the switch is closed, the sinusoidal pattern continues. Okay, the sinusoidal pattern continues. This is also known as an electronic momentum. So if assuming that LC, the interaction of LC is such that you have a high Q circuit or it has a large energy storage, even when the switch is off, the output still follows the sinusoidal trend. Now, the FET is modeled as a switch, as you can see, with a finite resistance R and an infinite off resistance. So when the switch was closed, you recall the capacitor charges up, and then when the switch is off, well, then since the LC energy storage elements have a high energy storage, it's a high Q LC tank. Now we don't have much damping, and it follows a sinusoid. That was a journal analysis, and the switching was done on a very small conduction angle. Okay, less than 90 degrees for high efficiencies, and we calculated these efficiencies, if you recall. So for conduction angles less than 90 degrees, and if you choose this small r over r as a small fraction, you have a very high efficiency reaching to 90%. Okay, but again, the analysis assumed an FET as an active device, and I told you that we were operating this as a switch in a saturation region where the current is not affected by the drain source supply. Okay, but it's only affected by the VGS, the gate source voltage. So as you are decreasing VGS, it becomes more and more negative. You can drive the transistor in the cutoff region. You can drive the transistor cutoff region. Okay, so this story is of an FET. Okay, so when you have a saturation region, when you are operating over here, it's a good conductor. It's a closed switch. Over here, it's an open switch. Okay, and this is an ohmic region where the current increases proportionally with VDS. Okay, but in saturation, the current is not being affected by VDS. Right? Okay, as you can see over here. Now, this is the story of a JFET, junction field effect transistor. What if this element is not a JFET? Okay, what if you replace this by a BJT? Okay, what if you replace this by a BJT, or still by conventional, let's say, vacuum tubes? What if this is replaced by a vacuum tube? Okay, so does this analysis for the calculation of efficiency changes? That's the question. Okay, so this question is addressed in the general analysis section of chapter 9, general analysis class C operation with non-ideal tube or a BJT transistor. So the above analysis that we have considered with FET is not valid. Why? Because these devices, which device is the ideal vacuum tube, non-ideal vacuum tube, or BJT bipolar junction transistor, they do not have a simple constant on resistance characteristic, which it implies they have a different IV characteristics, different characteristic curves. Okay, unlike the JFET, which we have seen over here. So the general analysis for evaluating the efficiency changes, right? The expression changes. So nevertheless, the nonlinear characteristics, nonlinear characteristics of tube and BJTs are specified graphically on their data sheets, and an accurate class C analysis, if they are using tube or BJTs, they can be done numerically. Okay, they can be done numerically by considering their characteristic IV curves. So the general analysis is the same. Okay, you consider the IV characteristics of BJT or vacuum tubes instead of JFETs, and you assume that for an LC circuit, which is going to provide you a flywheel effect, have enough Q to force the input and the output waveforms to be sinusoidal. So it's still a high Q LC tank circuit, providing enough energy storage, low damping. So you still have a nice sinusoid output. Okay, there's no damping. So that's the function of the LC tank circuit. Now, for this analysis, the device characteristics are plotted in a constant current format. So this, for example, this region we consider was a constant current format in the saturation region. Okay. So what we are going to do is, if you have a tube, for example, if you're going to consider a vacuum tube, in case of a tube, the curves of constant plate currents are plotted on a graph. Those axes are plate voltage and the grid voltage. So what is this plate and grid voltages? Let's have a look at this. There's a very interesting article in Electronic Design if you wish to read further about the tubes. I'll just explain it. I've taken this content from this article available online. So the basic concept of a tube is that it consists of two elements. First of all, just like a diode. So there is a cathode and then there is anode. Okay, so anode is called the plate of the tube, and this is an evacuated filament. It's an evacuated filament. So there is vacuum inside, and so there is a vacuum inside. So what happens is once you apply the charges connected to the battery, there is positive charges and the anode, and you have a cathode which is negatively charged element. So somehow you heat it up. Okay, there's a heating element which is not shown here in the schematic. So it heats up the cathode, and since we are putting charges, there is an effect called thermionic emission. Okay, that forms the basis of the working principle of vacuum tube. So what happens is, owing to this phenomenon of thermionic emission, when cathode is heated up in an evacuated filament, it loses some electrons, and owing to this thermal energy, the current flows from heated cathode to positively charged anode. So this constitutes the electric current. Okay, this constitutes the flow of those knocked out electrons from the heated cathode, and they start flowing towards the anode in the vacuum. And but again, if you recall from your brief past experience of electrical engineering, the conventional current is always from anode to cathode. That's how it is. But anyways, the electrons are flowing from cathode to anode physically, but the convention is the opposite. So this is the simplified diagram of a vacuum tube diode. You see why we call it a diode is because you recall that a normal, this is in the modern days, you have a semiconductor p-n junction diode, which only allows current to flow in one direction only. So you see the current is flown in one direction only, and there are only two elements. There is a p-type semiconductor and n-type semiconductor, and they are sandwiched to produce a depletion region where there are no carriers. So just like p-n diode, there are only two elements, and that's how the electron are flowing in one direction. So when the cathode is heated and the positive charge is applied to the anode, the electron can flow from the cathode to anode. So there's a separate heating source which is not shown here, but here it's more intuitive. You see in the inside of it, there is a heater. Okay, it's heating up the cathode, and then there's an anode. Okay, so this is cylindrical to provide more surface area, larger currents can be derived. So in a sense, still in the current applications of RF as RF transmitters, or in X-ray generations where large power is required, vacuum tubes are still preferred over small transistors. But again, since these after 1950s, transistors have largely replaced vacuum tubes, you cannot imagine fixing up billions of transistors which happen to work like as logic gates in a modern iPhone. You can't do that. Okay, you can't fix it up. You can put vacuum tubes there. Now, so you look at this diagram. This type of vacuum tube, it consists of only two electrodes, so it's still a diode. Okay, it's still a diode. So just like a semiconductor, p-n diode allows electric current to flow in one direction. The case of vacuum tube is quite similar. It's quite similar. So the electrodes in this depiction are arranged concentric cylinders within the tube, maximizing the surface area for electrons. So there's more current. Due to the more current, there is more plate supply voltage, which is the product of VI. So hence the cathode is heated by a separate heating element that is shown over here. Okay. So you see this. What does this statement say is that sinusoidal, if you assume sinusoidal plate and grid voltages, we'll look in a moment what the grid component element is. Sinusoidal and grid voltages are assumed, and a numerical integration of plate current, the anode current, the current that is received at the anode, multiplied by the anode voltage is what? It's the supply voltage. Okay, so this is equal to your supply voltage, right? And average through one complete cycle gives the power dissipated in the device. The power supply, which is the voltage times the average current, gives the total input power. Okay, that's the supplied power. And if you deduct from this power the power dissipated in the device, this gives the difference. This is the power delivered to the load. Okay, this is the power delivered to the load. So what the grid voltage is? Let's see. We have not seen the grid as of yet. Grid is a third electrode. Okay, it's in case of a grid. So what happens is that we have another you can say structure like this. This is a meshed filament or mesh metal electrode. This is grid. Okay, and let's say I have somehow I apply a negative supply, negative DC over here. So what happens is it has negative charge to it, and if I increase the negative supply voltage to the grid, it's going to repel the electrons. Okay, it's going to repel the electrons, and so much so that if this negative supply, let's call this V negative. Okay, if this V negative becomes large, we can derive this vacuum tube into the cutoff mode. So by controlling the V negative, we can control the flow of electrons. Okay, so we can derive this vacuum tube into a cutoff region. Okay, so the third metal which is inserted between anode and cathode of a vacuum filament, if we insert this third metal between anode and cathode, what we have is a triode tube. Okay, so before that it was a diode tube. Now this forms a triode tube. So the third triode called the control grid. This is the control grid. Okay, and how much power it can dissipate or handle, it's written in the data sheet again. So it enables the vacuum tube to be used not just as a rectifier, so that it flows the current in one direction, but also as an amplifier of the electrical signal. So we are just like a BJT, where you are BJT is a current amplifier. You see, you apply the current at the base, and the output collector current or the emitter current is beta times IB. Similarly, for example, so BJT is a current control device. Similarly, your junction field effect transistor, it's a voltage control device. Okay, you are controlling the channel width by controlling the VGS. So as VGS is decreased, so just look here, as VGS is decreased, it goes towards more and more negative. Okay, you are deriving this in a cutoff. Why is cutoff? Because you are decreasing the depletion width. So the depletion width of the channel width decreases for the JFET. Okay, so it's something like this over here. For example, if this is a P-type region, this is N-channel JFET. This is P-type region over here. There's another P-type region over here. Okay, and this is an N-channel. It's P-type, and let's say the channel is N-type. There are electrons over here, and you have a drain like this. This is my drain terminal, and then I have my source terminal over here. Okay, so if we connect them, we are going to connect these two terminals, let's say through a battery. There is a battery, positive terminal is a drain, negative terminal is a source. So first of all, if you're going to increase this, okay, there's more positive over here. Okay, and then there's a gradient. Okay, there's a gradient of voltage. For example, this is 4 volt, this is 4 volt, this is like 3 volt. So if this is your, let's tie this up together over here. There's no connection over here, and this, let's have this as negative. So your this terminal is the gate terminal. So you're going to reverse bias it. Okay, so as this is your VGS. Okay, so as VGS, which is of course less than 0, is increased, it's negative. So this is reverse biased. It's negative. The depletion width is going to increase. The depletion width is going to increase. As the depletion width is going to increase, you see the channel width reduces. Channel width reduces. The flow of electrons from drain to source reduces. Right. But this is what's happening over here. A very similar operation is is happens in the vacuum tube. For example, over here, as the grid voltage is increased, you are repelling the flow of electrons, and similarly, you're pushing the vacuum tube into the cutoff. Okay, so the control grid is placed between the cathode and anode, and in the shape of mesh, the holes that allow the electron to pass through it. By adjusting the voltage applied to the grid, you can control the number of electrons flowing from cathode to anode. If the grid is given a strong negative voltage, it repels the electron from the cathode and chokes the flow of current. Okay, so you can operate the vacuum tube as a switch, okay, as a switch on and off. So the more you increase the grid voltage, the more the electrons can pass through it. If it is for example, if you're connecting the positive of the battery, it's negative. If you connect the positive of the battery, it's the other way around. You have positive charges over here. Okay, in case you have positive charges over here, this becomes V positive. Okay, this becomes V positive. So as you are going to increase V positive, there are more electrons that are going to be attracted. Okay, so it controls the flow of electron basically, right? So more electrons can pass through it, and the higher the current. So this way, the triode can serve as an on-off switch for an electrical current, as well as a signal amplifier, of course. So this triode is useful for amplifying the signals because the small change in the control grid voltage leads to a large change in the plate current. Okay. So in this way, you see this is the control grid over here, and the positive charge is applied. So this is positively charged plate, and as you're increasing the V grid, as you're increasing the V grid, so as you increase the V grid, the current increases. This current is increasing. Okay. Note that the conventional current has an opposite direction to the current from cathode to anode, which happens, which is the physical flow of electrons. So in this way, a small signal in the grid, like a radio wave, can be converted into a much larger signal. So this is an amplifier, just like an NPN or PNP transistors. Again, its operation is, you see, it is just like VGS. The FET has an operation. It's a voltage control device. So you are controlling the channel width through VGS to allow the current or not to allow the current according to the channel width. Similarly, you are using the control grid over here. You're using the control grid with the control voltage V grid to allow or not allow the electrons to control the flow of electrons. So you are amplifying the signal in that sense. So note that you can also increase the plate current by increasing the plate voltage. Okay, you can increase, this is positively charged, this is anode plate voltage. You can increase the plate current by increasing the plate voltage, but you would have to change it by a greater amount. Okay, so in saturation you have to increase it by a greater amount than the grid voltage to achieve the same application of the current. Okay, so just look at these characteristic curve. For example, if the gate, so if the grid is negative, for example, this is minus 2.5. Okay, this is minus 5. This is minus 7.5. So if you are putting more negative charges on the grid, which is placed between the anode and cathode, you are repelling the flow of electron, and as a result, your current is decreasing. Okay, your current is decreasing, irrespective of increase in the plate voltage, in the anode voltage. So, for example, this region is your ohmic region. Okay, so this region is ohmic region. Why it is ohmic region? Because as you are increasing the plate voltage, the current is increasing. Okay, so more and more current, more and more flow of electrons from cathode to anode occurs, and there's more current. But then after you reach the constant current regions, increasing the plate voltage 10 volts, 20 volts is the current is not being affected much, but a minute change, for example, from minus 12.5 to 15 volts, a minute change can result in reduced current. Okay, so it's not much dependent on the plate voltage, but it's dependent on the grid voltage. Okay. So well, the development of the vacuum tube, it was in the earlier 20th century, 1900s, before the advent of the transistors in 1950s, where the transistors after 1950s have largely replaced the vacuum tubes. So, but still, nowadays, vacuum tubes, you will still find them in high power RF transmitters, since they can generate more power than semiconductor equivalent devices. So for this region, you still find the tubes. For example, in particle accelerators, more power is required, more current is required. You can find them in X-ray machines or CT scanners, which are 3D scanners as well. So, but the development of this vacuum tube was up until 1950, before the advent of transistors, and during those times, more versions of tubes were introduced. For example, further enhancement of vacuum tubes. The replacement of more additional grids. It's called screen grid, for example. So screen grid is between control grid and an anode, and it's given a fixed bias. Okay, let's call this, if it is, for example, a negatively biased, it consists of it made a electrostatic region. It forms electrostatic region between the control grid and anode, because it has own set of charges over here. Okay, so, and even yet another suppressor grid, which is even closer to the anode. Okay, so you can have more grids over here. So then for example, this, so over here with the control grid and the anode and cathode, this is called triode, with screen grid. This is screen grid. This is called a tetrode. And then you have a pentrode, and this continues. This is a suppressor grid. So why these developments happen was these extra grids actually solve some stability problems and they address other limitation. But just like within a triode design, the function largely remains the same. So the IV characteristics are largely the same. For example, over here the screen voltage is given as 200 volts, but that's how the characteristic curves are, and they look very similar to bipolar junction transistors or JFETs. So if you are coming back to the point, you see, if you are using this vacuum tubes instead of field effect transistors, okay, and where if you're replacing field effect transistors with vacuum tubes in class C amplifiers, where they do not have a simple constant on characteristic, then you have to consider the graphical data, okay, the graphical data, and you have to consider the nonlinear characteristics and the constant current regions, as we have used those regions in JFETs when they were in the class C amplifier. So instead, for the vacuum tubes, you will consider those nonlinear characteristics for plate current and for the plate voltages, right, to derive the efficiency of class C amplifier. So some drive considerations which are given in the textbook is that the class C amplifiers use, if they are using vacuum tubes, they nearly always drive the control grid positive. So when the tube is conducting, then the grid draws current and dissipates power. So the datasheet includes the grid current curves, so the designer can use the procedure outlined above to verify that the chosen operating cycle stays within both the maximum plate dissipation rating and the maximum grid dissipation rating. So these ratings are given in the numerical datasheet, so they have to be considered while designing. So again, a triode vacuum is, the analogy is very similar to, the curves are very similar to the NPN transistor. Here the tube plate is like a transistor's collector. Control grid is the base, okay, from which you are controlling the operation or the flow of current. You're controlling the current through the control grid, and then finally the anode is the emitter, which is emitting electrons while it is heated by thermionic emission, and the electron flows towards the anode in the vacuum or evacuated filament. The operation and the characteristics are very similar to of the vacuum tube, very similar to BJTs. But if you are going to use vacuum tube, you consider these characteristics, IV characteristics, the plate current and the plate voltage, instead of JFET saturation regions. Okay.